So when we talk about biology as a science, biology, by strict definition, is the study of life. Plain and simple. But how can we use good scientific method and process to study biology? Well, you may know different terms associated with science method without knowing that you were talking about the scientific method. So we break this down into inductive and deductive reasoning. If you induce something, okay, if you have an inductive rationale or reasoning behind something, it means that you are making observations, and from those observations, you're going to draw conclusions. You observe that it's raining outside. From that, you get your raincoat, your boots, and your umbrella, and off you go. Okay? It doesn't have to be complex. Deductive reasoning, however, we start to look at building what we call a hypothesis based on many theories and questions. And from that, we're going to actually design an experiment to accurately and adequately test that hypothesis. Now, from those experiments, you will do observations. From those observations, you will draw conclusions. But you see how this is just a little more complex, a little more structured and organized. And the deductive reasoning we start looking at as being important for building scientific studies. So a scientific theory is simply looking and taking a whole bunch of hypotheses that have been tested. We look at the conclusions from those hypotheses. We put those conclusions together with other conclusions, and perhaps many, 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 many conclusions. And if they're all reaching the same sort of basic conclusion, okay, so if they're all reaching sort of the same basic answer, be careful. I don't want to be too strict in our definitions here, okay? If they're all coming to sort of the same answer, the same end point, we can look at that now as something known as a theory. So a theory in biology or a theory in any science is trying to pull together a lot of hypotheses, a lot of data, a lot of studies that are going to support a common theme in biology. So we mentioned evolution being a common theme in biology, and we actually talk about the theory of evolution. And we can talk about how it is tested and how we have different answers from different tests and so on. And we can also talk about things like the theory of gravity. But we're not in physics, so we'll stick with theory of evolution and other biological-based terms so far. You do hypothesis testing every single day of your life. Now, no, you don't sit down and write out a hypothesis. But if you go out in the morning and you try to start your car and it won't start, what do you start thinking? Well, you can start putting together all kinds of questions, right? You can say, all right, well, maybe it doesn't have any gas. How can you check and test whether or not your car has gas? Well, hopefully the gas gauge is going to tell you, right? Okay. What about you turn the key and it makes a funny clicking noise? What might be wrong? Now, at this point, some of you may have just called AAA. But the rest of you that are trying to figure this out so you can get to class on time, maybe the battery's dead, right? So how would you test that? Well, see if the radio and the lights come on. If they come on, your battery's good, right? Well, before we get too far into thinking about the mechanics of your car, let's think about how this is a hypothesis. All of those things we stated could be hypotheses. My car doesn't start, therefore I think it might be the battery. Then I'd start testing. Do my lights come on? No. Does my radio come on? No. Okay, well then it's probably my battery. But I just went through and I wrote a hypothesis. In my head, at least. I tested the hypothesis. And when I tested it, if I can test it, it is what we call testable. And in a good scientific study, it also has to be falsifiable. Okay? Why does it have to be falsifiable? Well, this essentially means that I'm willing to be wrong. We don't want to write a hypothesis that we always know the right answer to, okay? We want these to kind of let the science lead us, not us lead the science. So when I said, all right, maybe my battery's dead, is it the end of the world if my battery's not dead? No, that's actually probably better, right? Or maybe not. Battery's kind of a simple fix. If it's not the battery, it could be something really expensive, right? So when we look at this process, we've got very basic things to start with. We will make these more complex later. Basic hypothesis. This is my hypothesis. I think Rufus chewed my shoe. It's a hypothesis. Why is it a hypothesis and not a fact and not a theory? And certainly not an answer. Well, unless you actually see Rufus chewing your shoe, you have no idea. That could have been chewed by a caterpillar. Could have been chewed by your baby brother. Who knows? Could have gotten caught in a sweeper. Who knows? Right? Unless you actually see Rufus chewing shoes. Then you have good support of your hypothesis that Rufus probably chewed your shoe. But until then, sorry folks, you're going to have to test that. Scientists have come up with all kinds of hypotheses, observations, and tried to put together good studies over time. We will think about many of these together and try to get a good hold on what it means to put together something like a controlled experiment. So we're going to have things like negative controls, positive controls, and experimental designs with variables so that we can actually test what's going on. We can have a better understanding of what is going on in a study. So we will spend a lot of time thinking about this. But in our general scientific method, we're going to make some observations. There's going to be some general observations. You go out, your car doesn't start. That's an observation. You start asking questions. Why doesn't my car start? Then you start actually putting together a testable hypothesis. Does my battery work? Do I have gas? All of these things. Then you experiment. You try things out. You eliminate the wrongs. And hopefully, eventually narrow it down to a conclusion where you've got a hypothesis that is not only a working hypothesis now, but one that gives you some answers. So you've got a hypothesis that says, all right, maybe my first hypothesis is that I don't have any gas. Well, maybe my gas gauge says it's totally full. So I reject that first one. I make a new hypothesis. My battery's dead. I start testing that. You're going to test it in different ways until eventually you're going to get to a point where you hopefully have an answer to your question. In this case, just a simple, why doesn't my car start? But in all of science, we're going to look for these good, testable, and falsifiable hypotheses. You have to be willing to be wrong. You have to have controls. You have to be able to do this again and again and again and get the same answer, and not just you, but anybody that wanted to repeat your experiment under the same conditions should be able to get the same answer. Okay? These conclusions that you draw need to be very specific for the hypothesis that you tested. They need to answer a question. But you've got to keep in mind that anything you do, as fabulous as it might be, one experiment rarely proves anything in biology. We test and test and test some more. And the whole idea is that with every question, there are many more questions that come about that are not answered yet. And that's the fun part of biology. And the fun part of science is that for every question, there are multiple more questions. And we keep going and plugging along until we find answers to all of them. And we'll spend a lot of time applying biology to your everyday life and thinking about how testing these ideas for what's going on in your food supply, whether or not you have fresh drinking water, whether or not we can get you the medical help that you need if you're sick. All of these things fall into the biology category. So we'll talk about a lot of things with this course. Can you finish this?